Okay. All right. Sorry, folks at home. We're doing, we already did example 5 on page 457, problem set 17.3. I forgot to turn on Screencast-O-Matic, so you missed that, but get with one of your classmates if you need to see that one. We're working on number 7 now, and it sounds like to me they have a wrong answer in the back of the book. Because it says the total force and direction on charge B. If I read the problem right and wrote it right, okay, A is a positive charge at the origin. B is a positive charge at 0.4 meters to the right. C is a negative charge, also further to the right at 0.75 meters. Okay? Now, without messing with any numbers, look at charges A and B. The force on B from A is to the right. It's got to be. And folks at home, if you wonder why we pause every now and then, our projector keeps blinking out on us. All right. The force on B from A has to be that direction, right? This is a positive charge, that's a positive charge. They're repelling each other, right? So B has to be feeling a force in that direction. C, on the other hand, is a negative charge located to the right. It's pulling B toward it. So there's no way that could be a negative direction. So my guess is we've done it right, they've done it wrong. Now, I didn't do the calculations, but I'll trust you to do those right. And no way the answer to A, parentheses A, can't be negative, and I think they just did it wrong. Okay, sorry about that. Okay, let's look now at the B question. Find the total force and direction on charge A. Okay, now I'm going to have to erase all my scribble at the bottom. Are y'all okay with that? Okay. Now before I do that though, let me think through and see if our magnitudes make sense. We've got twice as much force on B from C, and here's why. Number one, C is a stronger charge. Now it's not double, but it's about 50% stronger. Maybe a little more than that, right? From 3 to 4.6. So that's pulling even stronger. This distance is shorter, okay? 0.35, this was 0.4, okay? But then when you square it, that's even, in a sense, closer. I mean, the difference is, gets magnified. So I think I can believe that. I thought that was a little too much, but I believe that's probably right. Because you've increased the charge and decreased the distance. So I know it's going to be greater than this, but it's also going to be positive. There's no way the back of the book is right on that. Okay, I think they used this number, and I can't tell you why they gave it the wrong sign, but not right. Okay, so let's go to the B part. You okay with that? Ooh, why can I erase? What a pain in the neck. Remember when I said keep it? It's keeping it big time. So what I'm going to have to do now is redraw all this. I think I just and not save it. That's what I've got to do. Now open it back again, and now go back to this. And sorry about this. All right. Now I've got to change my pen back. Sorry about all the problems today. Okay, here's the origin, and this is charge A, and that was 3 microcoulombs. 3.00 times 10 to the minus 6 coulombs. I'm just going to write it that way. Okay. 1, 2, 3, 4, 5, 6, 7, 8. Okay. 2, 3, 4. This is 0.4 meters. Charge B, and that was 5.5. Yeah. 5.5 times 10 to the 5.50 times 10 to the minus 6 coulombs. And out here is charge C. That's 0.750 meters, right? And that's negative 4.60 times 10 to the minus 6 coulombs. So the B part of this one, find the total force and direction on charge A. So what are the forces on charge A? Where are they coming from? What is the force on charge A? Huh? From B. Okay, that's from 1. So the force on charge A from B, or B on A, whichever way you want to say it. I'm saying on A from B. I think that was backwards what I said before, but as long as you know what you're talking about. It's Q, which is 9.00 times 10 to the 9th Newton meter squared per coulomb squared, not degrees. Okay. And then the magnitude of the two charges, 3.00 times 10 to the minus 6 coulombs times 5.50 times 10 to the minus 6 coulombs divided by, you know, what's the point of doing this? We know the answer. This is exactly like the one we did before, and that was 0.93, was it? Newtons, right? But the difference is, what is the force on A from B? We know the magnitude. What's its direction? Yes, it's going to the left because these are like charges. Like charges repel. So B is pushing, okay, B is pushing A away from it, right? They're similar charges. They're the same signs, SIGN signs. So it's pushing it to the left. So that's, in this case, is a minus 0.93 newtons. Same numbers we had before, right? It's now the charge of, okay, yes?
That's what I was having a problem with. That's what I was asking you about. How do you know? I mean, because they're in the same direction.
Okay.
And both of them, I mean,
okay. Yeah, good question.
On them.
Okay. Remember this about charges and forces. Like charges repel each other, unlike charges attract each other.
Right.
Okay. So, since these are both positive charges, the force on that A was exerting on B has to be that way because it's pushing it away, right? They're like charges, repelling. The charge of B on A is pushing it away. So in this case, that's negative because it's in the negative direction, right? You look at the signs of the charges and say, are they attracting or repelling? And then depending on which one you're dealing with. Now here's the other thing.
But I was looking at both of them going that direction.
Okay, yeah.
In either case. So.
Yeah. Okay. But you see, the first question was, what is the force acting on B? Mm-hmm. Okay, two forces, one from A and one from C. Well, A is pushing B this way, because like you said, they're both pushing that way. So we're only interested in what A is doing to B. That's positive. What C is doing to B is attracting it. So that's positive. You see? You look at, it's the one it says on B. When you do on B, that's not, you're not worried about what it's doing to A or C. You're wondering about what A and C are doing to it. Okay? the force on that charge. Now, here's the other thing. Do y'all remember, didn't we talk about Newton's 3 laws way back in an earlier chapter? Okay. The third law was anytime one object exerts a force on the other exerts on that equal and opposite. So if A is pulling B, pushing B that way, B is pushing A that way. Equal and opposite. That's why the numbers are the same, but the directions are opposite. Because they're pushing, like you said, away from each other. So the force of B on A would be negative, but 0.93. Now let's do, and we didn't do this one before, so we'll have to, F of force on A by C. You could put by's in there if you want to, or whatever. That is 9.00 times 10 to the 9th Newton meter squared per coulomb squared times A is still 3.00 times 10 to the minus 6 coulombs. That's driving me nuts, and I'm not even looking at it. And now C is, don't forget, just the magnitude. You'll worry about direction later. 4.60 times 10 to the minus 6 coulombs divided by, and this is different too. What is the different distance between A and C? So, yeah, that's the 0.75, okay? Okay, 0.750 meters squared, okay? Now, I'll let you punch your numbers. Be sure you square that 0.75 in the denominator. The others are pretty easy to do, I think. First, give me a magnitude. Is it? Oh, you don't have a calculator? Okay. Sorry, I wish I had one. I'd let you borrow it, but I left it in the office. Anyone punched them in yet? We punch them in the South, okay. 9 EE or EXP 9 times 3 EE or EXP negative 6 times 4.6 EE or EXP negative 6 divided by 0.75 squared equal. It's going to be a pretty small number. Less than 0.93, I would say, by a pretty long shot. Okay, is that the 0.22? Is that what you said?
Yes.
Okay, 0.22. Now, what direction is it? The force on A by C. Which way is it pulling or pushing? It's attracting it. So it's pulling A this way, but it's a lot smaller. So that's in the positive direction. So when you add those two together, that should give 0.71 negative. Okay, in other words, B, am I pushing on the wrong thing? B is pushing it harder than C is pulling it. Because C is so far away, and C is less than B anyway. So it's not going to have nearly the pull, but reduces the force on it to a negative 0.71. Did they have that in the back for B?
They did have, well, they had positive 0.71.
What is wrong with them? There's no way that is. Okay. All right. I don't know what the problem is. All right. Now, I'm pretty sure if y'all have written all this down, we can do number C pretty easily. Let me read what C is. Find the total force and direction on charge C. Okay? The total force on charge C. We'll first do it from A. C from A is exactly the opposite of this one, right? This is a negative charge, but exactly the same magnitude, minus 0.22. You see why? A and C, same charge, same distance, same everything, except A is pulling C to the negative direction, so negative 0.22. Plus F of on charge C from B, and we did that in the earlier one. I've erased mine, but hopefully you still have it, don't you? When we did the force on B by C. That was 1.8 or something like that. 1.86 maybe? 1.86 Newton. But which way is B, what is B doing to C? Second? Yes, it's pulling it towards B. Let me point in that direction because I'm sitting here. Wait. Second? Yeah, because it's pulling it C in that direction. So that would be a negative. And you add those two together and you get negative 2.08. How can they get the other two wrong and get that one right? We're using the same numbers, you know.
So, when you're thinking about charges, do you always try to think of it in terms of an x-axis so that you...
Okay, this one's set up on the x-axis so that you only have one dimensional. Hopefully they'll never give you one that you're in a triangle or a circle or something else, because then you have all sorts of angles you have to worry with. Yeah, I think we're going to stay on the linear. Yeah. That way you always, it's either plus or minus, one direction or the other. You don't have any angles to worry with because we haven't done enough math to do the angles. Yeah. And they didn't do any examples with those either. All right. Any other questions? Does this answer these? And sorry the answers in the back were wrong, but I'm convinced we got them right, especially since that last one came out perfect. There's no way the others could have been what they said. Sorry about that. All right. Ready to start with example 3, bottom of page 475 in section 17.8. All right, for it, can I erase this? I hate to say this, and I really shouldn't. They were so concerned about the test, but they don't hang around to get this one. So they don't hang around to pay any attention to anything. But I'm sorry. Bad. All right. Yuck. We almost have to go back to example 2 and find the current through R2 in figure 17.44 and from example 2. Okay? Now, I'm going to sort of quickly, if I don't do anything quickly, but let me try. There's your battery. They call it E. You could call it V, whichever, is 90.0 volts. I don't want to run into a battery at 90 volts. That is one big, powerful battery. Okay. Going up here, and the current splits, and part of the current goes to resistor here, which we're calling R1. And that R1 is 23.0 ohms. Okay. Another part of the current goes through resistor 2, which is 14.0 ohms. Okay. And another part of the current goes through resistor 3, which is 5.00 ohms. Okay. They come back together and head back around the circuit until they come back to the battery. Okay, that's our drawing. That's our picture. It says find the current through R2 from that example, where R2 is 14.0 ohms, E is 90.0 volts, and for some reason they're calling, oh, V2 is the voltage across. They gave it away, didn't they? Okay, so we're looking for, you got some current, I1, that goes through R1, some current that goes through R2, and more current, other current that goes through R3. We're looking for this one, the one that goes through R2. Now, what I said they gave away, well, maybe they didn't. I'll see if you pick up on it. All right. This is what we're looking for, I2. We know what R2 is. We don't know where D2 is. Never mind this. Okay. Now, what is the voltage across R2? Put a voltmeter across R2 here. What's the voltage? You see? The voltage across R1 is 90. The voltage across R2 is 90. The voltage across R3 is 90. Because you got the same volt across all three. Remember, with a parallel circuit, the voltage, if it's a strictly pure parallel circuit, voltage across all the resistors is the same. The current splits, but the voltage is the same. In a series circuit, the voltage breaks down and splits, but the current's the same. Okay? But in a parallel circuit, the voltage across all three of those is 90 volts. And that's why they said in the book, equal V2. They gave it away because it's the voltage across R2. Make sense or not? Okay? So if you know the voltage and the resistor, is there any way to determine the current? We're only looking for I2. Anyone want to give me a hint?
The formula I2 equals voltage squared.
Not voltage squared, V2, sub 2, that's not a superscript 2, over R2, D2, no, okay. And that would be 90.0 volts divided by 14.0 ohms, and that would be what?
6.43.
Second?
6.43.
Oh, okay. 6.43, what unit? Amps. Very good. So at the very beginning, in example 2 that we did last time, we got the total current was 28.3 amps. Now we know that only 6.43 amps is going through R2. Well, the current, the total current is 28.3. So that means if that that's going through this is only that, and the total current here is 28.3, my word, where is all that current going? Anyone want to make a guess? Because this resistance so high, very little current, less than this. I would say not quite half of that. I would say maybe about 4 amps is going through R1. But because this resistor is so small, that's where the current goes. I always say current is like students. Always going for the path of least resistance, right?
So that current is always going for the path of least resistance.
Yes. Don't you think?
I don't know. I don't understand.
Well, if you think about it, water through a pipe. If you're squeezing this pipe, they're all connected together, and you squeeze this one, more water will come out of that one and less out of this one because there's more resistance here, right? Okay? Same type deal. because there's more resistance here, less current goes through there, maybe about 4, 6.43 goes there, and I bet you that would add to about 10, so about 13, 14 amps is probably going through R3. We could check that if we wanted to, if you're really that eager to check my ballpark figures, you could see that's the case. But let's turn the page and see if they ask us to do that. They got 6.43 amps too, by the way. Nope. The next one is a completely different problem. But if you want to do it, let's do it. Do 90 divided by 23. What do you get? Won't take long to punch that in. 90 divided by 23. 3 point what?
91.
Okay, almost 4. And do 90 divided by 5. Oh, I can do that in my head, can I?
18.
Huh?
18.
18. I said pretty close to 20. Okay. Yeah, that's where most of the current's going through R3 because it has the least resistance. There goes the current, student. Never mind. Okay. Ready for example 4? Page 476. If I can read, my eyes are giving me going crazy on me. So let's do a new drawing. Can I erase this one? You can? Okay. And by the way, I don't have my watch out, so y'all let me know. Well, there's a clock. Oh, we got plenty of time. All right. Example 4. Find the equivalent resistance and the value of R3 in the circuit shown in figure 1745, if I can read that. Okay? And for some reason, I don't know how this happens. The cord gets wrapped around the other cord. Okay. So here we have, oh, let me erase this. Is that okay? Everybody got it? Okay. Let's do our battery over here. That's 115 volts. That's not a battery, that's a generator. This is AC. You don't get 115 volts with a battery. But we'll let them. This is our E, okay? And it goes up here, and the current splits, and some current goes down here through R1, where R1 is 38.0 ohms. Okay. So more of the current comes over here to R2, and that's 49.0 ohms. Okay. 49, I can't read. Goodness gracious. This is aggravating. Okay. Okay. And then there's some more current goes over here to R3, and they don't tell us what R3 is. Oh, but they do tell us the total current leaving the battery, or the plug-in, and that I, the total current, is 7.00 amps. I say amps and write ohms. Something's wrong with the old brain. Amps. All right.
I think it's not.
It was just waiting for you to say something. It's just nuts. All right. Now, they gave it away by first asking you to find the equivalent resistance. What would be the equivalent resistance? Second?
Do you add up all the ohms?
Okay, that would be if it's a series circuit and you knew them all. This is a parallel circuit and you don't know them all. So you have to do a different approach here. What do we mean by equivalent resistance? That's if you took all these away and put one other resistor in its place, what would that resistor have to be? If you know the voltage, know the current, what would the equivalent resistance? Second?
We use the formula, we still use the formula, but we have to.
Okay, and what formula was that? Ohm's law. Okay, yeah, and that is, so the equivalent resistance for this circuit, without any of those in place, the R equivalent, I like to put EQ, the book, I don't remember what they use. They just use R, but equivalent resistance would be the total voltage over the total current, right? E, right? Ohm's law, E over I.
Very first thing, that'd be like then change it over, because I can only
Okay. All right. That would be if you plugged in a different resistor that was equivalent to all those three, even if you don't know the third one, it would have to be that, wouldn't it? Okay. So this would be 115 volts divided by 7.00 amps, and that would be what? A little louder.
16.43.
So let's just round it to 16.4 ohms, right? Now that we have the equivalent resistance, we can, this is the tougher math part, we can now get the resistance for R3. So now we look at the formula for equivalent resistance of a parallel circuit. And what would that be? That's that really weird one. The what?
I sub 2. How do you say I2?
Okay, we don't need that. We don't know what I2 is. Well, we could calculate I2, and you're absolutely right. Now that you come up with that, yes, that's one way to do it. Good choice. Maybe a little longer, but it is a good choice. Yes, we do know what I2 is because we know the voltage across, we can calculate I1 because we know the voltage across there and the resistor. We can calculate I2, this would be I1. We could calculate I2, and once we knew that, we could subtract and calculate I3. So this will certainly work, and then if you know I3 and E, you can figure out what R3 is. That is one way to do the problem. I hadn't even thought about doing that. That, I think, is probably mathematically going to be the easiest way to go.
I remember you saying something about that at the very beginning, but I can't remember. You know, I remember you saying something about I1, I2, you know.
Yeah.
But I can't remember.
Yeah. Well, you see, the current splits among the three paths. Okay? You see, this is the big current coming in. Some of it goes this way, some of it goes that way, and some of it goes that way. So the current has to split. You can't manufacture current, you can't do other. Voltage stays the same because the voltage across this is that, voltage across this is that, voltage across that is that. But the current splits, okay, because you got three different pathways. Okay? So I like the way you said it. The other way is really a pain in the neck. I bet you that's the way they do it. But this way is actually, I like your way. Okay? So what we're going to do, because we know the voltage across all three resistors is 115 volts. So let's figure what I1 is. E over R1. Wouldn't you say that's true? Isn't that what you were suggesting? Okay. And that would be 115 divided by 38.0. This is volts, and that's ohms. And that would be what? No more visual aids.
3.03.
3.03 amps. Okay, I2, because we also know it's E over R2, because this is a parallel circuit. That would be 115 volts over 49.0 ohms. And that would be less, wouldn't it? 2.35. 2.35 amps. Okay, add those two together and you get 5.38 and subtract that from 7.00 and that gives you 1.62 amps. That's how much goes, that's I3. And now you know that R3, what's its relationship between E and I3?
R3 equals.
Yeah, you know it.
It would equal E over
I3. Perfect. That would be 115 volts. Same voltage across there. And you know the current here is 1.62 amps. And that would give you what resistor? I know it's going to be greater than either one of those two, isn't it?
70.
Around 50? Huh?
70.
70.
70.99.
Okay, we'll just round that and have it as ohms. Now, since the others were right on the money, I bet you they want that to be 71. But it is 70.9, right?
It is.
Okay, let's see what they got in the book. They got 70.2. You know why? They did it the hard way. Okay? And I'll show you how they did it. This is how I knew they wanted you to do it. I didn't think about yours, which is actually, I think, a nicer way to do it. What, you going to say something?
No, I think that's why you showed us the very first time.
Okay, maybe. Okay? Because this is a pretty good way to do it. Here's what they did, though. The formula for the equivalent resistance of a parallel circuit, remember this one? 1 over Req. I call it equivalent. They just call it R. It's equal 1 over R1 plus 1 over R2. Remember this one? Plus 1 over R3. And remember what a pain in the neck this is to actually do? All those reciprocal trees and stuff like that. Well, we're looking for R3, so they have 1 over R3 is equal to 1 over R, they call it R equivalent, minus 1 over R1 minus 1 over R2. You just subtract these two from that one to give you 1 over R3. And since you know Req was 16.4, so you can do this on the calculator if you want to. Let's see what you get. 16.4 reciprocal, right? You know that key 1 over x or x to the minus 1, that key 16.4 reciprocal minus 38 reciprocal minus 49 reciprocal equal, and then take a reciprocal of that answer. Was I going too fast? Yay or nay?
No, you weren't.
I was too fast? Oh, okay. I'm a little surprised there's that big a difference between these two techniques, but it could be our way had more round-off error. That might be a little bit of it. What you get is the answer. Still not getting it?
I'm not getting what they got, but,
What did you get? Closer to what we got?
oh no, sir, I don't know what I'm doing, but that's okay.
Okay, let me do it. Let me do it a little more slowly and just punch them as I say them. Do you know what I mean by the reciprocal key?
I do.
It's 1 over x or x to the minus 1. Okay,
I'm doing it.
okay. Let's do it slowly. 16.4 reciprocal minus 38 reciprocal minus 49 reciprocal equals.
Correct.
Still not getting it. Oh, okay, no. But then at that point, do a reciprocal to your answer. That's it. Okay. And what do you get?
70.2.
70.2. Same thing they got. That makes me think we may have had a little round-off error in the way we did it. Okay? But close enough for government work. Okay. Yeah, that last one you have to do a reciprocal of the answer. All right. Okay. And in fact, you'll see exactly that, the keystrokes at the top of the next page. Is that right? Yeah, x to the minus 1. Either x to the minus 1 or 1 over x, depending on your calculator. Yeah, x to the minus 1 is a reciprocal key.
Okay, yeah.
Yeah. Okay. Any questions? All right. Ready to move onward? Okay. What I'm going to check on right now is I'm going to discard this. Is it okay to discard it? Y'all got it? Okay. And let's go to this one and see where we are on this side. Yes. Okay. I thought that's where we were. From current slide. So here is the summation. Hey. Oh man, I forgot to bring it. I got in a rush today. Sorry about that. Next Wednesday? Okay. Okay. Sorry about that. And say again your name? Yeah, okay, got it. Okay. Sorry. Okay. I had myself a note written down, but I didn't have a chance to sit and look at it because I had all those students coming in for advising. And I was in such a rush all day long, I didn't even get a chance to look at it. All right. Now, here is a nice summary slide for parallel circuits, pure parallel circuits. The currents add, because you have a different current going through each branch, so those add. The resistances add by reciprocals. What a pain in the neck. But that 1 over x t or x minus 1t makes it a lot easier, right? But you have to remember to hit it every time that you need to. The voltages, though, are the same throughout. Okay. So this is a parallel circuit. Okay. Now, let's think back to a series circuit where all these go through each other. In that one, the currents are the same. I is equal to I1 is equal to I2 is equal to I3 equal because the same current goes through every resistor. Okay? The resistances add not by reciprocals, but add. R equivalent is R1 plus R2 plus R3 because they're all adding more resistance to the circuit as you go. But the voltages also add. The total voltage is the voltage drop across R1 plus, across R1 plus the voltage across R2 plus the voltage, because the voltage splits. Some of it goes through the first one, some through the second. So, because remember what voltage is? Energy per charge. Same charge is going through all that. Some of the charge gets dropped, loses energy on the first one, more on the second, more on the third, so the voltages add. So you see, you sort of flip these two. In a series circuit, these are all equal. These add. In the parallel circuit, these add, and these are all equal. Now, resistors, in a series circuit, they add on top in the numerators, and in the parallel circuits, they add by the reciprocals in the denominators. So that's a big change there. But otherwise, these two kind of flip-flop, in a sense. Is that helpful or more confusing? You can always look it up. Okay. Okay. See what the next slide is. Okay.
Like on page 476, we did reciprocal.
476. Got it. Say again.
I was looking at the reciprocal.
Mm-hmm.
When we know to add and when we know to do the reciprocal, I think I know. Because we're trying to find it, so we have to subtract.
Right. Okay. Yeah. Let's go back to this. Is the equivalence equal to the sum of all the others? If you're looking for one of the others, then isolate that, start with 1 over r, and subtract the others till you get this one by itself. And then once you do that, you reciprocate again. Always have to wind up with reciprocating one more time. Your final answer. Is that what you were meaning?
I think I understand.
Okay. All right. Now, just a little bit of a verbiage at the end of this section. The parallel circuits are the ones you have to worry about, because like we just saw, if you thought about it, I've already, I think, done away with the slide. I think it did away with it. I'll go back and check. But you wrote it down. The equivalent resistance was something like 16, right? The individual resistors were 39, 48, 70-something. They were bigger. The equivalent resistance was less, meaning the current that had to go through there keeps adding. Okay? So you're if you plug more things in parallel to the same circuit, your current increases and increases and increases. And then if you didn't have a circuit breaker or a fuse, the wires would get so hot they catch on fire. And that does happen. And that's why they have circuit breakers and fuse boxes, okay? Because otherwise you burn the house down or whatever you have to be in. So that's the sort of the warning they do on the bottom of, not the bottom, sort of the middle part of page 477. That finishes 17.8. There's only 4 problems here, so do the odds anyway, because those 1 and 3. Okay? Now we're ready for compound circuits. Okay? Ugh. And this is where your whole concept of equivalency comes into play. Okay? A compound circuit contains a combination of resistances in series and parallel arrangements. To simplify that, you do equivalent resistances of whatever. Okay? So if this is your compound circuit, these two are in series with each other, but these two are in parallel with this one. You can't use one simple set of formula. So break them down. Let's take this, since these are in series with each other. What's the equivalent resistance between these two? Add them together. Then that makes what they call R4. If you plugged another resistor in instead of these two that was exactly the sum of those two, you'd have an equivalent resistor. Now that you have that, now you do your 1 over R4 plus 1 over R3 is equal to 1 over R5. You make the equivalent resistance to that, which is your reciprocal relationship. Right? Make sense? So that's how you go about solving compound circuits that have both series and parallel features or things in them. Okay? And that's all they tell you. So we'll go now to, okay, that was example 1. Sorry about that. and I talked through it, but here we'll actually write it down. Goodness, my eye hurts. Okay. That R4 here is equal to, because these are in series, R1 plus R2. Okay? And then R5 is 1 over R5, because these are two in parallel, is equal to 1 over R4 plus 1 over R3. And that's how you get the equivalent resistance to the entire thing. Okay? Now, if you wanted to go back, once you know all these things, you could go back and figure out. If you knew the voltage across it, you could calculate current through each one of them. Okay? All right. Now let's see. We're dealing with a different one. Let's see if they have this one on here too. All right, to move on. Ha! Yeah, it's on here. Amazing. This is example 2. Now you have R1 in series with the combination of R2 and R3 in parallel. Okay? So what you would do here is first find the equivalent resistance here between R2 and R3. And what would that relationship be? These are parallel. That's the reciprocal. And we're going to call that R4. So 1 over R4 is going to be R2 plus 1 over R3. Okay? That gives you R4. And then how do you get R5, the equivalent for all that? You add so R5 is equal to R1 plus R4, because those are in series with each other. Does that make sense? All right, good deal. These are going nicely. Any question on that? Now, let's see if they have example 3 here. No, they don't. Okay, sorry about that. So we're going to have to do this on our own. So what I'm going to do is discard that and pick back up on this one. 10 minutes we got. Okay. We'll go from current slide. Here's example 3. Find the total current in the circuit shown here. Okay. Here we have, we don't have red batteries, do we? Okay. We have black batteries. Okay. And that battery is not really a battery because the E is 115 volts. That's probably alternating current. You don't have voltages that high in direct currents generally. Okay? And that goes over here to, this is no different from what we were doing before. It's even simpler. Okay? This is not really a compound circuit, unless I'm reading it wrong. Okay? All right. And here we have R4. And here we have R3. And they tell us R3 is 19.0 ohms. I'm sorry, my eyes just really giving me big problems here. Okay. .0 ohms. Okay. Find the total current in this circuit. Okay. What would be your approach? Okay. You know, oh, wait. This is so bizarre. I was going to say you can't do it. Well, that's because they drew the first one to the right, and this is the, sorry about this. Okay. I was going to say this is an impossible problem. Okay. All right. The figure 1753 is over there on the right. I was thinking it was the one right under it. It's not. Okay. Okay. Sorry about that. Here is this one. It goes through R1, then through R2, and then down here you have R3. And they did give you what R1 was, 10 ohms. And they gave you what R2 was, 32 ohms. I can't write, my word. I'm going to blame it on my eye, but it's just, I guess I'm in a hurry. 32.0 ohms. I just didn't leave enough room there. And R3 down here is 19.0 ohms. Okay. That's the circuit we're supposed to figure the total current for. So what would you do? How would you approach that problem? Okay. And what do you, how do you get, you said you add them? So R1 plus R2 is going to be, we can call that R4 if you want to. You don't have to, but the equivalent of those two is 42. If I'm reading my lousy handwriting, 42.0 ohms. Okay? Now, we need the equivalent resistor between that one with R4 up there. I'm not going to redraw it, but just picture that instead of these two. Okay? Just imagine that as just one resistor. Okay? Then what do we do? Okay, and how do we do that? Reciprocal, okay? 1 over the equivalent resistance of those two then would be 1 over 42 plus 1 over 19. These are ohms, right? Remember at the end to do that reciprocal one more time. And what do you get? I guarantee you it's less than 19. Probably by a pretty good amount. Is what?
19. Wait, tell me again what to do.
Okay. Do 42 reciprocal plus 19 reciprocal. Now put equal and then do reciprocal.
We wouldn't do minus.
What's that?
So it wouldn't have been minus reciprocal.
Not here because you're, okay. The reason you did minus before, we were looking for one of the components, and that one component is the total minus, yeah, okay. Now we're looking for the total, which is this plus this plus this. I should be doing this.
13.08.
13.1, I'll call it, ohms. Okay, but I would leave the 0.8 in there because we're not really interested in that. We're interested in the current. So what's the current?
I equals E over R.
Okay, and that's the equivalent resistance, so that would be 115 volts. And I'd leave the 13.08. Isn't that what you had? Okay. Because the more precision you have there, you'll round at the end for the I. You don't round to every step. You get round-off error. What does that give you? Something about
8.79.
8.79? Yeah, that sounds reasonable. 8.79 amps. Okay? That's what we're looking for. Well, They got 8.78 because they rounded too soon. You were very wise not to. But that's close enough, again, for government work, okay? Because you're never going to get them. Well, I don't want to say that. I've never seen an ammeter that reads that precisely. I'm sure they make them. I just don't own one, okay? Want to try to squeeze one more in? Yay or nay?
Well, how far did we go in chapter 17?
You know, I just happened to think I should check on that.
There are a lot of sections.
17.9 is the end. So this is the last section we do. So we only have a page or two. You want me to go on and copy the quizzes test for you? Okay. Let me, and that's what we'll spend the rest of the time doing. So is it okay to go on and start uploading this? Since you don't want any more, okay?